So this is the 2017 autumn paper for the Maths for Cryptography, and it says calculate the multiplicative inverse of 5 in a Z18. So again, a Z18 is the integer set of all the remainders when all the integers are divided by 18. So the possible remainders are 0, 1, 2, 3, and right up to 17. They're all possible remainders. Now, in this case, we're looking for the multiplicative inverse of 5. So we're basically saying 5 multiplied by its multiplicative inverse, mod 18, divided by 18 will give a remainder of 1. So if we multiply 5 by some number and then divide it by 18, we should have 1 left over. Now, I don't know, there could be a mathematical formula for this, but the way I do it is I say, okay, I look at all the multiples of 18. So you have 18 by 1 is 18, 18 by 2 is 36, 18 by 3 is 54. And what I'm looking for is a number that when I add 1 to it will be divisible by 5. So 54 plus 1 is 55. 55, and 5 divides into that. Now 18 plus 1 is 19. 5 doesn't divide into that, that's no good. And 36 plus 1 is 37. 5 does not divide into that, that's no good, you see? So we have to have something that 5 divides into. The reason I'm adding the 1 here is because there's a remainder of 1 when we divide it by 18, and this is a multiple of 18, the 54. So I know that 5 multiplied by 11 is equal to 55. So 5 goes evenly into 55, right? So 5 times 11 are 55. Now if I divide 55 by 18, well, I've already figured out that 3 18s are 54. So 18 goes into 55 3 times, giving you 54. So you have a remainder of 1. So the remainder equals 1. That's this number here. So now you can say 5 times 11 is 55, right? Mod 18 equals 1. So I can say that the multiplicative inverse of 5 in Z18, when we're talking about modulo 18, is 11. And that's the answer. Okay? That's that one. Right then, let's try another type of question, where he looks for the greatest common divisor of two numbers. Right? Now, if the greatest common divisor of two numbers is 1, that means 1 is the only number that will divide into them, then they're prime to each other, i.e. relatively prime, so they can have a multiplicative inverse. Right? If two numbers are not relatively prime, that means that they have a greatest common divisor that is greater than 1. So, for example, if I was to have a look at, for example, 8 and 12, and I was to say find the greatest common divisor of 8 and 12, right? Well, all the divisors of 8 are 1, 2, 4, and 8. They're all the numbers that divide evenly into 8. And divisors of 12 are 1, 2, 3, 4, 6, and 12. They all divide into 12. So you can see they have common divisors of 1 and of 2 and of 4, right? Now, if you have to find a multiplicative inverse, that means you have to find a remainder of 1 when, say, 8 is divided into 12, or 12 divides into multiples of 8, sorry. So, but if you look at 8, you've got 8, and the multiples of 8 are 8, 16, 24, 32, 40, 48, 56, and so on. And the multiples of 12 are 12, 24, 36, 48, 60, and so on. So you can see there's no way that the difference between these is going to be 1, that you're going to have a remainder of 1, because that goes into that, they are the same. And the difference between these other numbers is like 4 between them all. So you're not going to have a difference or a remainder of 1. So if you have to have two numbers that are relatively prime, they'll have a greatest common divisor of 1, and then one can be the multiplicative inverse of the other. So sometimes you're just asked to find if two numbers are relatively prime, or rather asked to find the greatest common denominator, or the greatest common divisor. So for example, in 2018 autumn, question 2, you're asked to find the greatest common divisor of 87 and 111. So, and then the question was, in Z 111, does the element 87 have a multiplicative inverse? And explain. Note, it doesn't ask you to find the multiplicative inverse, just to find it. Now, these numbers are really big, so trying to find the common divisor, all the divisors of 87 and of 111 could be quite hard. So I'm going to use an algorithm, Euclid's algorithm. And it's basically provided these two numbers are not 0, right? So just say we have to find the greatest common divisor of two numbers, one's called A and one's called B, and we want to make sure that A does not equal 0 and B does not equal 0 first of all. Then we can say that A is equal to B multiplied by some number, Q, plus a remainder. And that the greatest common divisor of AB is also the greatest common divisor of BR. And then we repeat this. That's why it's an algorithm, because we keep repeating these steps over and over. So now we're going to find the greatest common divisor of 87 and 111. So you say, well, 87, how many times does it go into 111? It goes in once, with a remainder of 24. So I can say that 111 is equal to 87 multiplied by 1 plus 24. So now you can take this number here and this number here, and we can say that the greatest common divisor of 87 and 111 is the same as the greatest common divisor of 87 and 24. And now we can repeat this, and we can do 24 into 87. How many times does that go? Well, 3 24s are 72. So we can say it goes in 3 times. That gives us 72. And we have a remainder here of 15. So I can say that 87 is equal to 24 multiplied by 3 plus 15. Now it's the same as that one, and now we can get this. So that means now the greatest common divisor of 87 and 111, which is also of 87 and 24, is now the greatest common divisor of 24 and 15. And I do it again. Although these numbers are small enough, now I could probably just get the divisor because 24 and 15 are small, but we'll do it one more time. 15 into 24 goes once. Take away the 15 and find out that we have a remainder of 9. So we can say that 24 is equal to 15 multiplied by 1 plus 9. Now we can take these two, and we can say that the greatest common divisor of 24 and 15 is now the same as the greatest common divisor of 15 and 9. And at this stage, you can say that, well, the multiples of 15 are 1, 3, 5, and 15. And the multiples of 9 are 1, 3, and 9. So we have 3 as the greatest common divisor. So we go back to our original numbers, 111 and 87, and I can now say that the greatest common divisor of 87 and 111 is 3. Now that means they're not relatively prime. So there is no multiplicative inverse for 87 in Z111. And if you wanted to check, you could say, does 3 go into 87? Well, actually, just as a check, but we did the algorithm right. 3 into 87 goes twice, remainder 2, 29. So that goes into 27 9 times, 29. Right? And then, oh, hold on, 3 into 87, yeah. And then 3 into 111. 3 goes into 11. It goes into 9. 3 times, remainder 2, 37. So yeah, 3 does go into these two numbers. It is the biggest common divisor. Because it's greater than 1, they're not relatively prime, and there is no multiplicative inverse for 87 in Z111. Thanks.